Dr. Ed Buie. Ed is an expert in the circumgalactic medium. Atmospheres are things we can all relate to, right? We need it to live. It engulfs the Earth, and it determines a lot of the history of the Earth. You have to understand the atmosphere is part of that. Planets have atmospheres. Stars have atmospheres. Galaxies too. They have atmospheres. It's called the circumgalactic medium. Except for it's invisible and very hard to constrain. And to understand it, you have to do computer simulations. And Ed is an expert in these simulations. He's going to tell us all about them. Ed's kind of a remarkable person. I think he decides he's going to do something and then he just goes for that. So just to talk a little bit about his path, I think some students might relate to that. He started out in accountancy, actually, as an undergrad, and then he took at Michigan State, and he took a course from Megan Donahue, who is a co-author of a book that many of us use. It was that course, right? And then he said, you know what I'm going to do? I'm going to go into astrophysics. And within I think it was 2.5 years, was it? Or 3 years? 2.5 years, he was already taking his first graduate course in astrophysics. And he came here and he did his degree here at CC. He graduated 3 years ago now. Mm-hmm. And charted his own path there, said, yeah, I want to be faculty, but I want to have a real teaching focus. So he did some work developing courses. And then he eventually graduated and became a professor at Vassar, where he is today. And he has got a teaching focus, but he still continues to also focus on some fascinating research that he's going to tell us about today. So with that, I will turn it over to Professor Ed Buie.
Well, thank you everybody for having me today. It's a pleasure to be back. I love Arizona, especially this time of year. Right now, New York is frigid, so it's been a nice time to be here enjoying the warmth. So yeah, today talk about a theoretical view of turbulence and magnetic fields in the CGM of galaxies. And because I was here, I know that disciplines widely vary, and so kind of wanted to start on something we're all familiar with. Good old sun. In the summer, it's like the bane of everybody's existence here. In the winter, it's very pleasant. In New York, I've learned to very much appreciate it in the winter. Keeps me a touch warm. And so we have our solar system, got the sun, all various planets and such. And if we want to think about the distance from the sun to the outer edge of the solar system, it's about 6 trillion miles or so, or 50,000 astronomical units, with an astronomical unit being the distance between the Earth and the sun. So pretty big distance to cover there, but that's just in our solar system, of course. And so we can zoom out to even further distances. There are other stars out there besides our sun. And so we can look at this stellar region around our sun. This one is about 30 light years across. This is about 40 times bigger than the radius of our solar system. Now, many other stars out there. All of these stars around us lie within our home galaxy, our good old Milky Way, this being about 3,500 times bigger than that stellar region from earlier. And our Milky Way is about 100,000 light years across, or 30 kiloparsec. So every time we move out bigger and bigger distances, make up a new unit so that we don't have to see all these huge numbers so much. Our sun lies about midway between the center of the Milky Way and the edge of the disk. This is bright blue, a lot of massive young stars in that disk that are yielding their light, make it shine blue. And for a while, when we thought of galaxies, that's kind of what we thought about. When we looked out into space, what we saw, like Evan said, there's an atmosphere around galaxies, but back in time, wasn't so easy to observe it. And there was always kind of a theoretical framework around it. People imagine that there probably was a cloud of gas around a galaxy. If you look at the rate at which stars form, there's only so much gas in a galaxy, right? And so all those stars have to come from that gas. And if it was just limited to the gas within that galaxy, galaxies would have stopped forming stars a long time ago. And so there's a theoretical framework for there being a cloud of gas surrounding a galaxy. As technology improved, we now know the picture looks more like this, where you have our central galaxy in the middle, surrounded by this halo of gas called the circumgalactic medium, or CGM for short. This CGM is about 20 times or so bigger than the central galaxy, and it plays a huge role in dictating how that central galaxy evolves over billions of years. As stars form within that galaxy, most massive ones are going to explode in supernova, die, launch their ejecta out into that CGM. It's going to pollute it, mix with the gas already there. Eventually, it's going to recycle, come back down, make its way back into the galaxy to form more stars, meteors, and all that good stuff we know and love all around us. We can also have gas that comes from beyond this CGM in the intergalactic medium. This gas tends to be extremely diffuse, very metal poor. Also, anything heavier than hydrogen and helium, astronomers call metals. So there's very little of those elements really far out in this accreting gas. And so this helps us to tease out what gas is coming into the galaxy versus what gas has been recycled. And very dynamic place. So how do we observe this halo surrounding galaxies? So we use quasars. These are hyperactive supermassive black holes. I like to refer to them as space lasers. And in the middle of the quasar, you have a supermassive black hole. Now I can actually show an image of it. We have like more of these popping up all the time now. It's kind of crazy what we can do, technology. And so you have matter that is circling this supermassive black hole. Some of that matter falls in, and the matter that does, some of its mass is outright converted into energy, so it's very bright, and that light shines throughout space. On its way through space, it interacts with various clouds on its way to us. Each cloud has different amounts of gas within it, and some of that gas, depending on what's in it, is going to absorb specific frequencies or wavelengths of light. And so by the time we observe it on Earth, we see the culmination of all that, where we have these dark bands of light that has been absorbed by the gas between us and that object. And so here I'm showing a bunch of halo surveys that have been done. There's more going on now. A lot of these have been done with Hubble. On the y-axis, you can think of this as the amount of the gas listed in that lower corner. So this is H1, that's neutral hydrogen. More of it, you kind of see, and then the x-axis distance away from the central galaxy. And we see neutral hydrogen, there's so much hydrogen in the universe, most dominant element in the universe. So we see that pretty much regularly all the way throughout that CGM. We can look at another ion. This is magnesium 2. Magnesium with one of its outer electrons removed. Takes a little bit of energy to remove an electron from an atom. But we tend to see magnesium 2 more closely associated with in the inner CGM, closer to that host galaxy. And we can look at something a little bit hotter, oxygen 6. This is oxygen with 5 of its outer electrons removed. It takes a bit more energy to remove all those extra electrons from the atom. And so this is tracing much hotter gas. And we kind of see this oxygen 6 all dispersed throughout the halo. And so this starts to help paint a picture for what this CGM looks like, where you have this atmosphere of gas with colder clouds dispersed kind of in towards the center, near the central galaxy. And those colder clouds are being traced by that magnesium 2, while the hotter ambient gas is traced by not only neutral hydrogen, but also oxygen 6, because there's so much hydrogen. So hydrogen's going to tell you about everything. And I like to think that when I was first learning about this, kind of similar to Earth's atmosphere, you have the ambient atmospheric gas and they have clouds embedded within it that are colder than the atmosphere itself. And those clouds will eventually accumulate more and more water vapor, rain down on the Earth, and then process, rinse, repeat. And modeling helps us to understand how this halo evolves over billions of years. When folks do those types of observations that I showed you earlier, those are what are called pencil beam observations. And they only tell you about that narrow beam of light, that the narrow beam that light passed through within that halo. But if you get lucky, you can find a lot of these different beams to kind of build a picture for what is happening. Emission is very hard to measure from this CGM, although now technology is improving where we're starting to be able to make these what are called emission maps. So you get a large scale view of how the gas throughout the CGM is orchestrated, what is what temperature, what is at what density. But putting the two together as far as, okay, you have a picture in time, and then how does that evolve over billions of years from now? And how do they even get to what it is now? So that's what I do, model. So in essence, I like to say I stir a really hot gas. So stir some hot gas, the input of energy that generates this 3D turbulence in a three-dimensional box. This encourages the mixing of energy, heat, and matter throughout that box. I also shine some background light on it. In reality, this light is coming from the accumulation of all these active black holes within space. And all their light shines on these halos around different galaxies. And the model that I use tracks the non-equilibrium cooling and ionization of all these atoms within this box. And so visual representation, got some turbulent feedback, plus some background radiation, gets me my box that is mixing up a bunch of gas. So we'll start by looking at the halo dynamics in an environment with and without turbulent feedback to get a baseline for how that turbulent feedback influences the galaxy's halo. And I did mention this before, but that turbulence is in reality is generated by the stars that are forming within that disk, generating so much energy is propagating throughout this halo. You could also have a very active supermassive black hole that is also moving matter within this halo that is mixing it up more and more. And so we'll look at with and without that turbulent feedback to get a better gauge on how this mixing influences that halo. Then we'll start to compare some magnetohydrodynamic or MHD and hydrodynamic simulations. The magneto part just means it considers magnetic fields as well. And we'll look at that on large and small scales to see how things differ. And then lastly, we'll look at some metallicity differences. So first, I'm presenting some work done with by some students that I work with this past summer, Param, Uman, and Sam. They looked at halos with and without turbulent feedback. So each simulation includes halo co-rotation. So folks have looked at the magnesium-2 absorption of clouds around a galaxy and found that those tend to rotate similarly to how the central galaxy rotates. And so we included that. And then magnetic fields as well. So showing two sets of simulations, and they're evolving over time. I wonder, could you guess which one is which? Oh, then I ask. The one behind me, who thinks that has feedback? Raise your hand. Yeah, you would be correct. Yeah. So one behind me, feedback, fairly obvious, is a much messier picture. You have a lot of gas that is getting flung around in all these different filamentary structures, mixing with the ambient material already there. Whereas when you don't have feedback, it's a very clean system, very symmetric. And I remember when we first did this, another student that was coming by, she had commented on it. She was like, "Oh, it's a really pretty galaxy." I was like, "Huh." And so now, like the folder that holds all the information for this simulation, it's called Pretty Galaxy. I was like, "That's good." Yeah. The other ones don't look that nice. So when you have a bunch of gas in a box doing a bunch of stuff, one good thing to do in the beginning is to plot it all up on a temperature density phase space. So on the y-axis, you have the temperature of the gas. The x-axis is the density. And the color bar is showing you how much mass is within each temperature density bin. So the blue parts is a lot of mass lying within those temperature density ranges. And then red, not a lot of gas lies there. And feedback is behind me on your left, and then no feedback on your right. And immediately it becomes apparent that you have all this material where when you don't have turbulent feedback is not there in this temperature density phase space. So all this gas at intermediate temperatures, low densities, and also a range of densities that's fairly cold, you don't see it so much when you don't have turbulent feedback. So that turbulence is giving you a lot of mixing that is leading to these different intermediate states of gas in this temperature density phase space. And even the portion where there's a bunch of mass around almost 1,000,000 Kelvin, slightly cooler when you don't have turbulent feedback. So that turbulence is giving you some extra heat that is also heating up your ambient halo gas and raising the temperature of the ambient halo gas to slightly above 1,000,000 Kelvin there. And without it, that ambient halo gas, large collection of blue mass, is slightly cooler and spans a bit wider range of densities as well. You can also look at neutral hydrogen. Since it's so prominent in the universe, might as well look at it. And with feedback, again, very messy. A lot of filamentary structures extending way far out to the edge of the CGM. Whereas without feedback, it's pretty much very concentrated in the center, and it starts to trace some of these spiral arms that also extend fairly far out into the halo. You can also look at something very hot. So this is highly ionized oxygen. This is oxygen 6. And with feedback, you can kind of see it kind of traces the outlying, almost like a membrane of these filamentary structures. And without feedback, when it's only rotation, you have much more of it that cleanly traces these very extended spiral arm structures. And we do observe spiral arms in galaxies, but they don't go out that far. So this is kind of like an extreme case that you wouldn't see in nature. And we also see much more oxygen 6 kind of tracing the ambient halo gas as well. So, and that is because that ambient gas is slightly cooler, and this cooler temperature happens to align better with the oxygen 6 ionization state. Another thing students looked at was the magnetic field within these halos. This is not something we expected to see. I mean, I also didn't have really any expectation of what this would look like, but definitely didn't expect this. So when you don't have feedback, we find that the magnetic field within that halo builds up quite rapidly and just keeps going up. Whereas when you have feedback turbulence that is mixing this material up, those magnetic field strengths don't stay so high within that halo. And here I'm just showing a plot of that magnetic field strength over time. The green curve is the simulation without feedback, so just rotation. The black curve has the turbulent feedback and rotation. And see that with feedback rapidly increases and then falls off over time. As that magnetic field saturates, those magnetic field vectors starting to cancel each other out, and magnetic field just decreases over time. And when you have no feedback, it just rapidly increases, and it just keeps, presumably would have kept going up. That was something we did not expect, and they found quite interesting. We also looked at the radial velocity comparison. So each snapshot is showing further and further in time. So as things are moving forward in time, you see gases spreading out, taking up more of this phase space. So the y-axis is the radial velocity. Positive values is gas that is moving outwards from the center. Negative values is gas that is moving inwards towards the center. And this time the color bar is showing what's called plasma beta. So this is a ratio of the thermal pressure to magnetic pressure. So red is really hot, low magnetic pressure, low magnetic field strength. Blue, super cold, high magnetic field strength that dominate there. And very different between these cases. And especially without the feedback, we see a lot of that inflowing gas, the gas with negative velocities, tends to be highly magnetized. So now with that out of the way, what if we looked at the same turbulent feedback, but now with and without magnetic fields? So now let's say we turned off the magnetic fields, what happens to that galaxy situation? So here, have two simulations going. The one on your left has magnetic fields, the one on your right does not have magnetic fields, and nice visualization of how these halos evolve over time. And you see most of the gas still concentrated in the middle. You still see a bunch of these filamentary structures that extend all throughout the halo, a bunch of clouds that kind of form and eventually condense, and gas that is falling back on into the center again. And I will say this is probably my favorite part of what I do. This is why I wanted to do theoretical stuff, because even if, I mean, technically all simulations are wrong because they don't consider everything. And so, but they give you a better idea of what's happening in that situation if you consider certain physics. And so even if you do something way wrong, you at least still get to see something cool. So I was like, all right, I get a little reward for the effort that I put in. I'm good with that. When I did observation, I looked at something and I got a dot. I was like, all right, spend a whole night for this dot. I guess I feel happy about that. So here I am showing neutral hydrogen. The top row is showing you from the hydrodynamic case. The bottom row is showing you MHD with magnetic fields. The first column is from a face-on perspective. The second column is from the edge-on perspective. And we already noticed some differences here. So without magnetic fields, the cooling gas tends to break up more easily into smaller clouds that are dispersed throughout that halo. And then also with magnetic fields, it tends to facilitate a flatter central disk structure in the middle there. And we will come back to this central disk shortly. So keep that in your mind. We call that foreshadowing. Before that, though, it's important to note that the magnetic field tends to be tied to the matter. So wherever there's high densities, you tend to have high magnetic field strength. And that makes sense. The matter is what allows that magnetic field to propagate throughout. And so you have more material, you're going to have more magnetic fields building up in those areas. And especially at these very high temperatures, you have a lot of free electrons, a lot of charged particles, and those are allowing the propagation of more magnetic fields throughout. So here I foreshadowed this. This is a plot of the angular momentum. And then the x-axis is the distance from the center. Your black line is showing you what you would expect for the angular momentum if you were expecting simple Keplerian rotation around the center. And yellow, where a lot of mass is, purple, not a lot of mass. And then this first column is earlier in time. The second column is slightly later in time. So you can see the difference of how the mass moves about that black curve. And we notice that the top row, again, is hydro. And so the magnetic fields also tend to lead to a central disk that not only is flatter, but it spins faster than without those magnetic fields. So it seems that these magnetic fields are allowing the gas to transfer angular momentum more effectively throughout the material, collecting in towards the center. And so kind of gets sped up as it's falling in towards the center. So now what about smaller scales though? So these are some simulations that I did within the past month or so. And so here is one case looking at the denser material closer into the central disk. And these are on very small scale. So the full box is a couple hundred kiloparsecs. These boxes now are about 100 parsecs on each side. So very, very small portion of this entire volume. And so on small scale, this is showing you the density for the hydro at the top and the MAC at the bottom. And for the most part, at least by eye, they look fairly similar. We don't see much difference between the two. Now, of course, we want to run more in-depth analysis to quantify how different or similar the two cases are on the density level, but it seems that with the initial look, they seem to be fairly similar to each other. Where you have, filamentary structures, really dense gas moving around, and then these kind of void structures, low density pockets there. And this is an example with 100 kilometers per second of turbulence. So this is a highly turbulent box. There are cases we have that are not moving quite that rapidly. And so in those cases, it might be different, but we have to see. And then we also look at the temperature, and the temperature does look quite different. When you don't have those magnetic fields, it seems that the temperature of that gas is slightly lower. So the top row is a bit cooler on average there. And this is probably most likely influenced by the additional winding and twisting of magnetic field lines, adds another injection of heat to the gas overall. We can instead look at some more intermediate densities, so some stuff that's a bit further out at lower densities, see how that gas looks. The temperature on these smaller scales seems to be more comparable when you are looking at gas that is at lower densities. But the density differences also seem to be fairly comparable. So it almost seems that if we're considering the lower density gas within the halo, whether you have magnetic fields or not, don't make quite the biggest of differences between the two cases. But again, preliminary results, I'm gonna do some more analysis to quantify how similar or different are these two cases on this small scale. And last but not least, we gonna look at some comparisons between different metallices in this mayhem model. And this is some work that is being done by another of our students, Mariah Jones. So here are some density volume readings of 30% solar, 70% solar, and 100% solar gas. In all cases, gas is highly concentrated in the center, but and then you have these filamentary structures extending far out. At this particular snapshot in time, I forget what time this is at, it seems that the 100% solar case has kind of more dispersed structures further out within that halo. And again, we have a bunch of gas evolving in a box plotted on a density temperature phase plot. So temperature on the y-axis, densities on the x-axis, metallicity are the same as before. And we notice as this metallicity is increased, we get more and more gas at lower temperatures at a range of densities that is less prevalent in our 30% solar case. I also looked at the total cooling evolution in the halo. Black, solar metallicity gas, blue, 70% solar. The gold, orangish color is 30% solar. And this over time. And we did not expect is that at late times, it seemed that the lower metallicity halo had the largest amount of cooling. And this is contrary to our expectations because your metal lines are what allowing you to get more and more cooling happening within this halo. And so we expect it to be the reverse, where if you have higher metallicity, we would get more cooling within the halo at late times. And so I thought about like, okay, maybe this has to do with hydrogen cooling of the gas, because all right, well, you have more metals in our higher metallicity case, which means there's less hydrogen there, slightly less. And so there's a prominent hydrogen cooling around 10 to the 4 Kelvin. And so I thought, okay, maybe there's a large buildup of hydrogen gas around 10 to the 4 Kelvin in that 30% solar metallicity case in this 6 to 7 billion year time frame. So we looked at that. So plotting again the cooling on the y-axis, on the x-axis is the distance. The first plot is at 6 gigayears. The second plot is at 7 gigayears. So we can see how these curves change over this 1 billion year time frame. And you can see that at 7 gigayears now we have this 30% solar metallicity case that has a bump in cooling around 50 kiloparsecs from the center in that 30% solar metallicity run. So now we started to isolate what is causing this increase in total cooling that we found in this halo at this time. And then got a bunch of phase plots here. On the y-axis, cooling, x-axis this time is temperature, and then the color is tracing the mass. We have 30% solar, middle 70%. Your far right is 100%. And the top row is at 6 gigayears, bottom row is at 7, so 1 billion years later. And if you turn your eyes to this top corner here, you notice in a 30% solar case, you have a lot of mass that's collected around 10 to the 4 Kelvin. As you get to higher metallicities, we don't see all that mass build up around that temperature anymore. it tends to cool to colder temperatures. And so it seems that when you have more metals available in this gas, the gas is able to cool to these lower temperatures and not build up around 10 to the 4 Kelvin. Now, this is something that one did not expect to see. It's cool to find it in this model because it might be a consequence of us not having considered every different channel that gas can cool by. So if we put in more cooling channels for different elements, then this feature at 30% solar might go away. That's something that we want to explore later on. And last but not least, we also wondered, what if we decrease the initial magnetic field in the halo? How might that influence things? And one thing I hope you're kind of gaining from this is that, at least for me, when you do theory, you kind of just like change a lot of these different knobs. Like that's the fun of theory. You just change knobs and see what happens. So on your left, we have, this starts with 0.1 microgauss. So this is the highest, this is the higher magnetic field strength. And then on your right is 10 to the negative 3 microgauss. And it's just showing a volume rendering of how these halos evolve over time. Just by eye, they look fairly similar. And so we think like, oh, okay, well, maybe considering a lower magnetic field strength 100 times left doesn't matter much. And maybe it doesn't. Sneak peek, it does. So we did this for different metallicity. So the top row is the higher magnetic field, bottom row is the lower magnetic field. Metallicities are shown there just to kind of see what each halo snapshot looks like at 7.6 billion years. All of them look kind of similar to each other. And so we'll look at some more distinct differences between the two. So here are some magnetic field slices from a face-on perspective. And the color is showing you the magnetic field strength. So yellow is high strength, deep purple is low magnetic field strength, and then the black lines are showing you the magnetic field lines themselves. In the center, for all of them, magnetic field is pretty comparable, on the order of 10 plus microgauss. But we noticed when we considered lower magnetic fields, so this bottom row here, those field lines tend to be much more tangled within that circumgalactic medium. And also, the strength of that field in that CGM tends to be lower on average. And if you look really closely, you can also see like these coherent magnetic field like kind of flows in the top row. And something we also looked at was the velocity field of this gas, and it tends to follow these magnetic field flows that you see on the top row. This is the magnetic field evolution within that halo. So the strengths on the y-axis across time. Our solid curves happen at the or start at the initial magnetic field strength, 0.1 microgauss. The dashed lines begin with the magnetic field strength at 10 to the negative 3 microgauss. And see, it starts much lower, and then over time rises, and eventually saturates over time around 5 gigayears. Whereas if you started really high, peaks, and then kind of maintains that high level of magnetic field strength within that halo. And this type of growth that we observe on the bottom two curves is kind of more typical of what other theoretical studies have seen when they consider magnetic fields. And so it turns out when you put in your initial magnetic field strength, whatever value you choose matters a ton. Now, this is looking at that magnetic field across radius. And again, with the higher magnetic initial magnetic field, and these the higher metallicity runs tends to have a higher magnetic field strength. And we can make that make sense. We think of more metallicity, more metals. These metals are going to have more electrons. If it's really hot, more free electrons, higher magnetic field strengths. But when you have this lower initial magnetic field, that trend starts to get reversed. And so now the lower metallicity run tends to have a higher magnetic field strength as we move further out. So instead of the black curve being above the gold, when you have lower initial magnetic fields, those reverse. And so now we have the gold above the black lines, we get further out into the halo. And not quite sure why that happens. Still something that we have to look more into. So yeah, this is something we recently found out. And another thing that I have realized as a faculty member now is that like you do a lot of stuff at some point in time, and then the semester starts and like you have responsibilities, and then you forget the stuff you did, and then months go by and you're like, oh yeah, I forgot I did that. And then you're like, oh, let me look at that a little bit. You do a little bit more, and then the semester starts again, and you forget. And then time goes on and on and on. And you hope that you wrote something down from the last time you looked at it, so you can go back and you don't have to rediscover. I have learned to do that now. Some of this stuff I have rediscovered, but I don't know why this happened. So this is a new thing I'm going to be looking at with some students this upcoming semester. So just want to quickly go over some things we learned together. Galaxies have an invisible halo of gas surrounding them, helps to regulate the central galaxy's evolution over time. Gas flows inward and outward and gets recycled within this halo, very important to that galaxy's evolution throughout time. All these processes tend to mix cold and hot gas, and that can generate turbulence. This being really jump-started by the star formation that happens within the central galaxy itself. When rotation dominates and we don't have much feedback, the halo becomes much less dynamic, becomes much cooler, and you have much higher magnetic field growth throughout. And when you compare the MHD versus hydrodynamic, the MHD tends to help protect cold clouds from mixing with ambient gas, facilitates a flatter central disk structure. We saw that there are more those clouds that broke up when you didn't have magnetic fields. There's more mixing between that gas. There's other plots I forgot to show that would have illustrated that, but MHD also enables warmer pockets of gas at higher densities, but there tends to be minimal differences in the densities between this material. And we want to go a step further and quantify how similar are the two cases. And then the initial magnetic field that we consider definitely matters. And last but not least, large scale simulations, mayhem with 30% solar metallicity gas tend to experience this large buildup of mass near 10 to the 4 Kelvin. And we want to see, okay, how often does this happen? And for instance, if we consider slightly higher metallicities, slightly lower metallicities, is there a range of metallicities around 30 where we get this effect at? If we have more cooling processes we consider, does this go away? Or is it more enhanced? I don't know. More things to learn. We always have to learn more about the model that we used. So thank you for having me. I'll put all these back up again. It's a pleasure to be here. And before I finish talking, the last thing I want to say that I want to leave you all with is the most important thing. Last semester I was on sabbatical. The most important thing I learned from those travels, had a lot of adventures I can get into later, but the biggest thing I learned from that is that humanity is going towards not only a better future, but the best possible future for everyone. I firmly believe that. A lot of evidence happened while I was traveling that made me come up with that theory. And so now I'll spend the rest of my life realizing that in the short lifetime that I have. But that's it. All right.
Okay, we have time for some questions. So if anybody has questions, you can raise your hand. We'll run a mic to you.
Yeah. Just a reminder that people in 4 or something class.
If you're in the SES 401 or 501 class, please do not run away right now, or just stay after the question. Thank you.
Yeah, that. Stay.
Hey, Ed, I got a question for you.
Hey, Tom.
Just wondering how much compute resources you have access to and how long it takes to run these. And what would you do if you had, say, 100 times more compute resources? like, all these NVIDIA AI training data centers and all that.
Yeah.
What if you had a big giant chunk of time on one of those? What could you do with it?
Yeah, that's a great question. So yeah, if I had like pretty much unlimited resources, I would run my large scale simulations with higher resolution because higher resolution is always better. And if they're really good, and they just do that faster. Right now, the large scale simulations, they have about 1 kiloparsec resolution, and to run it through 9 billion years takes about a week and a half to 2 weeks, depending. The small scale happens much faster though, depending on the resolution. Evan and I, we did some like really high resolution ones. I don't, it was like half a parsec maybe or something like that. I don't know, but those take quite a while longer. But on average, a couple days to a week or two for the small scale ones. So yeah, if I had unlimited time, higher resolution, both of those, because why not? Put in more processes to consider. And I started to have a lot of fun with it. Start to vary some things. Like the simulations they consider like a constant metallicity, but of course reality is not that varying metallicity. So we'd throw that in. More processes of like the stellar radiation background, things of that nature, how that would affect things. Yeah.
I'm not sure you can hear me. Oh, there we
Yes.
go. Excellent. I had a question about this last point that you have on the slide right here about that 30% gas having that large buildup. I know that you said you need to kind of look into adding more cooling lines and seeing if that sticks around. Have you thought about what implications it would have if that does stick around? Like, have you thought about how you might interpret that information as it currently stands?
How would I interpret that? So if it's still stuck around after I put in more cooling lines and like I said, I want to model gas at slightly higher, slightly lower. If it's still stuck around then the next thing I would do is really dedicate some time to coding in a metallicity gradient. So be highest at the center, low as you fall out, and I don't know, make some curve to quantify that change. And then I'll run that. I would not expect to see it there. But if I still saw it there, then it's like, okay, this is weird. And now I'm going to talk to some other theorists to see, like, have they ever seen anything like this? And yeah, we'd have a big kumbaya session, talk that out.
There we go. You gave us a lot of possible worlds with the different simulations. Could you speak a little bit about what kinds of constraints observations have provided on this, if any? Are some of these obviously implausible based on current observations, or are they too low resolution to know?
Yeah, that's a good question. So the observations have they inform what metallicity I consider. So so that 30% solar is about the average metallicity of CGM around nearby star forming galaxies. Like I said, though, it varies throughout the halo, but that tends to be the average. It also, those absorption line observations, you can separate out the turbulent velocity portion that is giving you the line, some of that line width, and that helps to inform how much turbulence we inject in our simulations there. And so we use that to constrain how much we stir it, essentially. And so we go back here. Yeah, there we go. Okay. The small scale ones, for instance, this is happening at starting at a constant 100 kilometers per second. that would be that's very turbulent gas on the high end. There have been some observations that have seen that, but that's like really, really high. Most of them tend to be less than that. And so we have some that are they had a range from like 10 to 50 to 60 and eventually 100. In the box itself, the turbulence varies by radius. So it's strongest in the center and then weaker as you go away from the center. That being informed by star forming galaxies, most of that turbulence being generated from stars forming and going off. And so that's going to happen in near towards the center in the central galaxy. We don't see much stars forming further out. And so those observations helped me to build this model to inform those initial conditions going forward. And as far as going back to learn more about the observations with the modeling, we can plot things like this. This is a neutral hydrogen column density. So this is happening in 3 dimensions, but you can collapse it down into 2 dimensions. So you add up, you integrate everything along line of sights. And astronomers do this when we take those absorption line measurements. And so you get this quantity from those absorption line measurements. And so you can compare the 2 against each other to see how close are you. And from a simulation perspective, you know what in your model led to those column densities, whereas when you're observing it, that's what you see. And you can make you can have a hypothesis on what led to that, but you don't know for sure. So the modeling kind of helps to inform, okay, how did I get this situation that I'm observing?
Yeah, hey, Ed, awesome talk. Beautiful images. Could you go back to your conclusion slide?
Yes, I'm sorry for this rapid pace.
Yeah, so you kind of started to address it. I wonder if you could continue along those lines. Because your model is making very specific predictions here, like the higher the magnetic field, the more cool clouds exist, and like, all these sorts of things. So like, is there a suite of observations you can imagine in the future that could actually see if some of these correlations that your model suggests actually happen? Is that something you're imagining? And if so, what?
I should be better about that. Sometimes I live too much in theory land. I just want to do stuff and then be like, all right, here, observers, does this match anything you're doing? So one thing that we're doing that I am looking at more is the small scale simulations. The reason being is because like they have much higher resolution that is more comparable with the observations that people can find as far as resolving power. And so you could do a better comparison between the 2. And so one thing that I've been looking at to do is look at the velocities of different parcels of gas in relation to each other and plot that to see how those velocities vary across the box, and then compare that with what folks observe from their observations. Because the magnetic fields might change that a good amount, and it might be more in line with observations or not. That's not something I know. And I don't know if folks know that. So, yeah.
Yeah, thanks. That sounds really interesting.
Where are you?
Okay, I'll start.
Thanks. That was a great talk. Just by looking at the words you use, my background's civil engineering. So as I'm trying to use the filter and absorb this, I'm looking at a water pump. So there's pumps designed for volume. There's other pumps designed for pressure. So in your theory, in your thinking, and you're looking at this, do those 2 words come up when it comes to the magnetic fields?
That's such an interesting interpretation. This why I like CC. You get stuff like that. I never thought about that before. Huh? Oh, I don't know. Yeah, I don't know. I mean, huh. So like just thinking about it now, like okay, like I could say okay, let's take some section of the simulation and just look at over time how does the magnetic field strength in this volume evolve over time, and how does that pressure change, and if are the two correlated to one another? Yeah, yeah. I mean that's interesting. Yeah, I like that insight.
Hello. Yeah, thanks for the talk. I wanted to ask about the components of like the physical counterparts of the components that went into modeling the feedback. Like, is it a combination of AGN, stellar, supernova, or something else? Like, what are
Yeah.
the specific components?
Yeah, a good question. So in this case, there aren't any stars, so no supernova, no AGN on it. That in reality, that would be what is causing this turbulence. And so in this model, you kind of we use the turbulence almost as a shortcut to replicate that CGM turbulent environment that people observe without modeling the particles and the processes themselves that lead to those things. So this way, it speeds stuff up, so we don't have to consider those things themselves, but that also limits what inferences we can make from this modeling. So you always got to keep that in mind. Yeah.
For the initial magnetic field, just in my mind, how I'm imagining that's been modeled, that it starts at a lower point and then eventually meets where the other models are. So how does that initial magnetic field evolve over time, and how long does it take to start meeting up with the other models where you aren't changing the initial magnetic field?
Mm-hmm. Yeah, good question. So in reality, what has happened, there's something called the turbulent dynamo effect. And so those small low magnetic field strengths, they're being, as the matter is moving about, it's twisting those magnetic field lines. And so initially, the simulations have a magnetic field only in the Z direction. But as time goes forward, you start to get magnetic fields being propagated into the Y and X direction, which is having this positive feedback on the Z direction magnetic field. So they all grow together until eventually they get to the end, until eventually they get to this point that is comparable to the ones that are a higher magnetic field. And that happened around 5 gigayears or so. All right. I fulfilled my duties. No, I'm joking.